Good morning. Welcome to the session. Thanks for coming in. I lead the language processing and execution group in the SQL Server Relational Engine. What we're responsible for is taking SQL as it comes in off the wire, comes up through the netlibs into open data services. We take it from there. We parse the SQL statements. We normalize the SQL statements, and by that I mean do semantically equivalent transforms into a canonical form that's easier to operate on, and also explain a couple of the neat tricks we do with it to do with view management, things like that. We're responsible for binding, which is name resolution within your given context. We drive the optimizer. We get the result back from the optimizer. We manage the stored procedure cache and the statement cache. We drive query execution, and we return the results back down that same path through the netlibs that I talked about earlier. We're also responsible for the T-SQL language and for where we're going with T-SQL into the future. We plan big changes from within the engine with respect to programmability, both in T-SQL, but way beyond T-SQL. Looking at supporting many languages in the server. It's a real focus of ours, and I'll spend a little bit of time on that. We're also responsible for the full-text search access method, and finally, we're responsible for shared disk cluster failover. That's sort of the whole package this team's responsible for. I'm going to talk about what's being delivered in the relational engine, which is this team, including the optimizer and execution. I'm going to talk a little bit at the start about what 7.0 has done and how it's positioned us for the future. And then I'm going to go through most of the interesting features, some of the ones that I think are really hot. Features that I think are really important are index views, materialized views. I'm going to talk about index views a fair amount, and some partition view support as well. There's a whole lot of features to cover. In fact, we're kind of proud of the current rate of innovation that we're putting into the server. And it's a good time for us. I've been in the industry now for about 14 years. I've been in Microsoft 3 years. Prior to that, I was lead architect for IBM with DB2. And you know, each release is kind of the same. You go through a period of excitement at the beginning of a release, big plans, big objectives, and it's really fun to watch new features come online. And towards the end of the release, it's slogging and slogging and slogging, day after day, polishing, and polishing. And we've been polishing this product. You know, the product that we're about to ship this summer, we've been polishing it now for better than half a year. We're just about to ship beta again. Finally, our heads are coming up, and it's wonderful for me to look out across this audience to be able to tell you about what we've done. It's a good time for us because finally we're going to get a chance to see the light of day and see this thing roll out. And I probably shouldn't be whining. It's only been 18 months, but it seems like a long time. Now, my focus, of course, has always been database. It probably always will be database. But one of the things I have to remember is this release is a whole family of Microsoft releases. And the part that's most interesting is the core of this family is Windows 2000. A lot of new features in Windows 2000. It's a very important release for us. But you know what's important to me from a database perspective? This is the single most stable, robust operating systems release ever done by the Microsoft company. It's astounding. I've been running this thing on my laptop for 2.5 years. All of the development work throughout Shiloh release, SQL Server 2000, was done on Windows 2000. We have a fundamental step forward in reliability and robustness in the underlying platform that we're building upon. And that is needed for us to, again, make the improvements that we want to make in underlying stability as well. This release, driven by requirements across a fairly broad range of areas, including business operations, data warehousing, knowledge management, and of course, it's built on SQL 7 as the core. The basis for all this work is SQL 7. Now, SQL 7 was a seminal release for the SQL Server team. And by that I mean it's a release that you only do about once every decade. In fact, some database vendors never get to do a release like this. It's true. In fact, funny thing is when the SQL Server 7 started, there was about 5 major database players. There isn't 5 anymore. And the reasoning behind that, in my opinion, is products that don't position themselves for the long haul, those products that don't aim for architectural cleanliness in their core product, those that jam features in too fast and aren't thinking enough to the future, they go away. 7 was a very painful, very long release for the team that was involved, but the dividends are paying huge now. We had a team working on 7 and continuing into this release that come from a very broad background. We have folks from Tandem, IBM, Digital, Informix, Oracle, Sybase, Britton Lee, on into obscurity. Having that experience says we know we have to have the discipline to focus on the core infrastructure and keep it strong, because that's what people buy in a database. The features are important, and I'm going to talk about features today, but features are worth nothing without stability. So we've really focused on the stability, and payment for that stability is in this release. This is the, 7.0 was a down payment. What you can see, I'm going to take you through the features that we're delivering in the 8.0 in the relational engine space today. And one thing you'll see is in just over a year, look at how much we've put into the engine. And the reason behind that is that we invested in 7.0, we invested in the architecture. We'll keep doing that. Here's a rundown of some of the features that were part of 7.0. As I said, engineered for the long haul. And the real test of the long haul is the next release. That's this release. As I step through the features for SQL Server 2000, I'm going to break them into 5 main areas. I'm going to look at first the programmability, and that's a really important area for us. Programmability is one of our core mantras. In fact, if you look at the things that my team believes are most important, it's number 1, programmability, and our long-term focus. We have a multi-release plan of wildly richening the programming model that we support in the server, supporting all common programming languages in the server, using exactly the same development and debug environment in the server, and making a very extensible server. And I'll talk about some of the first release of that multi-release plan during the course of today. Second big mantra for our team is wildly expanding the class of applications that can be efficiently written on a relational database. And by that I mean, relational databases have been around for 30 years now, but we need to expand the class of apps that can be efficiently supported on these relational databases. So I'll talk about some of the things we're doing there. That's a second big mantra of ours. And the third one, and this is one that keeps coming up, and every presenter better talk about this, and that's performance and scalability, but this time without the administrative costs that's normally associated with that. So those are 3 things that we're always thinking about. Second thing we'll talk about today is XML support. Then we'll look at manageability, get into scalability and performance, and finally look at some of the fairly substantial changes that my team's made in the areas of shared disk availability. Diving down into programmability, here's the features that we're going to be looking at there. Some of these are big requirements that have been around for quite a while now. We're really glad to have the infrastructure necessary to be able to answer these requirements. Looking first at cascaded referential integrity. We support now the ANSI standards semantics for cascaded RI for both deletes and for updates. I show an example at the bottom of this slide. You'll see the first table declaration is for country. The second table definition is for employee. And notice employee has a nationality that references back to country. It's a foreign key for country. Third table definition, that of renewal reminder at the bottom, has a different form of referential integrity. Notice the foreign key is declared there instead of being with each field. It's declared at the bottom of the table definition and shows 2 fields referencing back into employee. Now the semantics on this is if I were to make a change right now in country, for example, change a country name from, say, USA, change it to be US, that would propagate throughout the system, propagate down that referential hierarchy. If I were to do a delete, same thing, it propagates down. It's very powerful. Previously, this was possible, but the way it was typically implemented is using triggers. This is a much more natural way to express that, and it doesn't clutter up the trigger space. Our opinion is that triggers are very powerful. Active database is a very powerful way of adding extensibility to a database management system, but you don't want to clutter up the trigger space with standard function. So implementing DRI as a built-in is the right answer, rather than forcing people to implement it in triggers. User-defined functions. This is an extremely important one, and remember I was talking about this multi-release plan for adding more programmability into the engine. This is an extremely powerful feature, although initially when you look at it, it looks fairly small. It's part of our making the engine much more extensible, allowing customer code to tailor the engine and actually run in the engine. What the user-defined function is there's two possible forms of a user-defined function. The first one is a scalar function. So what that does is that takes an argument of 0 or more arguments and produces a single scalar result. It can be used in a select list, so you can project out select of a function foo of, say, column C1 and C2. And what that allows you to do is to do transforms in the select list. Anything you can write in T-SQL, you can now write as a function and put it in the select list. You can also use these in, for example, in a where clause. So you can say where function f of C4 greater than 16. Another form of user-defined function is a table function, a relational user-defined function. And what that does, it's a function, same as a scalar, except this time it produces a possibly multi-column, possibly multi-row result. So anywhere where you can use a standard named table or view today, you can now write a function. This one's remarkably powerful in that it allows you to do joins between functions and other tables and other views in the system. This form of extensibility is very powerful because it allows an application developer to build this function directly into the server rather than paying client-server interactions. And it's a way of richening up the semantic level in the server. It's amazing what you can do with just these two features. For example, one vendor that added user-defined functions, I don't think this was necessarily the right way to do it, but they wanted to be able to add full-text search support because all of us support full-text search. They were a little behind. They added full-text search, the access method, to their engine using user-defined functions only. Fairly impressive that that's even possible. So it goes to show you the kinds of power that these things have. And just the same way that you can have views over tables, you can have views over functions and functions over views, and everything composes the way it's supposed to compose in a standard relational database system. So it's a nice orthogonal extension. What we'll keep doing is extending this support. Today the support is T-SQL because that's our internal stored procedure language. In the future, we will support other languages as well. We'll always support T-SQL, we know it, we love it, but we'll also support other languages as well. In fact, as I said, this release is coming to a close. I've had the next release, a small team working on the next release for almost a year now, because it's fairly substantial support that we're adding, and that's in the area of programmability and supporting multiple languages. We believe, one of the best virtual machine teams in the entire world working on this problem. And I'm getting early performance results in now, and it's pretty exciting. What we're seeing is T-SQL, which we've been running it for as long as we've had the product, running competitively with other languages, other general purpose languages. That says that we're going to be successful delivering this function, this power, in more than one language. Very excited about that. Here's an example of a user-defined function, just to make this a little bit more concrete. This particular example takes, as an argument, a two-part name, like, for example, James Hamilton, and an integer argument, 1 or 2. And you could write this function a lot tighter. But what I'm aiming to do is to show the kinds of things that are possible. So it's written using a case statement. And you can see that what it does is if you pass in 1, you'll get out James, if you pass in James Hamilton, or pass in 2, and you get out the second name. So this is a trivial example of the kind of data transforms that are possible. And you could build a view on top of this, and the function entirely disappears at that point. So it's a great way of composing or adding features directly into the database engine. Column level collations. Two reasons that we're talking about this, probably three. First reason is server consolidations. Paul talked in his keynote address about bringing different apps or different databases onto the same server. Previously, we had server-level collations, which made that very difficult. If you were using different collation sequences or different sort orders, it was impossible to do that. So that's one reason to do it. Second reason is multi-language applications or international applications, where you have some customers in one country and some other customers in another country. And it's important for that same central data to support both. Because what lives longer than programs is data. Data lives forever. Programs come, maybe takes them 5 years to go away, but data lasts forever. And so having the flexibility to support different collations inside the same database is really important. So we've gone from server level down to database level, and in fact, we went a heck of a lot finer than that. What we did is we went down to a column level. Now, I told you three reasons for talking about this. That was two of them. The third reason is it was so hard to implement, I had to talk about it. This one was anticipated to be terribly difficult, and it was worse. It was a really tough one. Leahy did a phenomenal job of getting this together, and during the keynote, it really made my day, because to be honest with you, it's hard for some of us core engine guys to get excited about, we know that international issues are so important, but it's not the most exciting function in the world. I was sitting beside a gentleman, and when Paul mentioned column level collations, the guy that had been silent throughout the whole presentation sat up and said, "That's great." And I just went, "Yes, thank you, thank you." So, good news. What we've got is collations at the column level. So within the same table, this is really industry-leading function, you can have different orders inside the same table. A lot of flexibility in what you can do with that. And rather than, let's just look at an example to show you what's possible. The first statement, this is new support already, is that I can now create a database with a different default collation than the server. That's good news. Good to be able to do that. And to be honest with you, I think this probably is a 60% case, maybe a 70% case, is just being able to have control at the database level is very good. Second example, I'm going to create a table. Now there's three fields in that table. First one, product ID, picks up a default collation, because standard declaration without any additional syntax picks up the database level collation. Good news, as it should. The second two are kind of interesting in that they declare different collations. So now I have three different collations on the table products. So the first thing is I can declare collations at database level, then I can declare them at an object level, and now I can even change the collations at a statement level. So let's look at statement 3. Statement 3, I'm doing a selection from that table. But in this case, I'm not specifying any collations, so I get the sort order of the underlying defined table. Statement 4 is kind of interesting in that even though the table definition was right at one time, let's say it's not right now. Or let's say it's not right for this particular application, or let's say it's not right for this application running in this particular locale. Then you can add a collation sequence to it, and that changes. So now the order that you'll get back is now appropriate for the locale, in this case, French CIAI, is appropriate for that locale. Fifth example, same kind of thing. It's specifying the collation order that you want back for that particular data. A couple reasons this is important. One is it gives a lot of control, and that's important. And the second thing is it allows evolution. So the underlying schema may have a specific sort order. It's nice to be able to control it at an application level, because as applications evolve, there may come a time when you want to change between one collation and one sort order and another. And this allows the new application to actually specify what it wants. So reasonably powerful. Instead of triggers. This is great. I mentioned index views were great. I mentioned partition views are great. Here's another one that's great. One of the problems you get with relational database systems is good application developers use views, right? Good application developers understand that rule I said earlier that says, you know, the only thing that lives longer than those old snarly old programs are data. Data lives forever. And so you like to have views to protect applications from underlying schema change. It's very important. Now, what are the two problems with views? Well, there's two problems, right? The one problem is you can't afford to give up performance. Second problem with views is the darn things are more often than not updatable. And so the lie is visible. We'd like to tell you in the relational world that you feel like you're operating on the base table, but everyone knows when you go to insert into that base table, it's not a base table. So that's two problems with views. Problem one, that was the performance issue, is totally addressed. Remember I told you there's some neat tricks that go along in normalization? After we parse a SQL statement during normalization, one of the things we're doing is we transform the statement into a form that's amenable to optimization. One of the things that we do is we take the entire view definition, you know, select from multiple tables, whatever, and just replace the view statement with the actual definition of the view. What that does is it means the optimizer sees not just the original query, but the entire query with the view. That means the optimizer has the power to optimize and pull predicates past view boundaries. Extremely powerful. And what that means is how much more do views cost than direct access? Nothing. There's no difference. There can't be a difference because of what I told you. So the first thing we've got beat. That is the performance issue. What about the second issue, the visibility of the lie? I can't update, I can't insert into half the views. There's two solutions there. It's part A and a part B thing. The part A solution is that all relational database vendors, if we're worth our salt, should always be extending the classes of views that we can update directly. And we all do. Some do it better than others. But we all do it. That's one thing. The second thing is there's a whole class of views that are just provably not updatable. Doesn't matter how smart you are, there is no way you can update this view, and it's never going to change. That's where instead of triggers come in, or that's one of the places where instead of triggers come in. Instead of triggers allow you to make every view updatable if you know a way of disambiguating it. Very powerful. What it allows you to do is when an insert comes into a view, if you've defined an instead of trigger on it, then your T-SQL code gets control. You get to see the change that was being attempted, and you get to redrive that against base tables as appropriate. And I'll show you an example of a second. So with the performance problem solved and instead of triggers, I think what we've got is real view support finally. And again, this gets back to what I was talking about earlier. What are our core mantras? One of them is programmability, making the system easy to use. And this is, to me, this is one of the things. We all know that views are a good idea, so make them work. You'll keep hearing that kind of focus from us, and that's 100% where we are here. I'll give you an example of an instead of trigger performing view management. I'll give you an example of that in a second. But there's a second purpose of instead of triggers, and that is, effectively, they're a before trigger. They're a statement level before trigger. And so because it looked useful to us, we said, well, listen, rather than just supporting instead of triggers on views, why not support them on base tables as well? Two reasons to do that. One is, well, it gives me before triggers, and that's useful. And the second reason is, what's the most frustrating thing when you're using a database product? Non-orthogonal function. Function where, you look on page 237, part C, and it says you can use this except if you're using this particular data type in this particular environment. So it's the wrong answer. So supporting instead of triggers on base tables as well as views just continues to make views more real. So we support it there as well. Here's an example. Now this example is going to come up in different guises over the course of the talk. The reason for it is I'm in love with union all views. And the reason for it is union all views are another very powerful construct that can be for administering a data management system. One of the ways that it comes up is partition views. And I'll talk later about some really good stuff that we've done with partition views. And the way a partition view works is that you have, for example, all of January data in one table, all of February in another table, all of December in a final table, and you've declared a view over top of that. I'll show you some support a little bit later that's, in fact, handles that case transparently with optimization and even in the cross-machine case. So we'll save that. Let's take a simpler example for this case. Here we've got a view over 3 different regions. Very, very typical example. You've got 3 regional offices. They maintain their own database. They possibly maintain their own server. And each one has their own tables. To be able to run queries against that, very common case, use a union all view, and you have a table that appears to span all of those. More powerful than that, I mean, that's a good thing, but the ability to be able to directly update that view previously wasn't possible, because in this particular view, where only one base table was modified, it's potential. But in more complicated views, where an insert could affect multiple base tables, those are the cases where you really can't update them. There's no way of doing that. Let's look at how we handle this case. We're going to define a trigger. The trigger is on that overall view that spans those 3 base tables. And what we do is when you insert into that base table, or delete or update or whatever, when you into that view, pardon me, this code gets control. In the case of this particular trigger is declared on insert. We give you control, and we give you the inserts that were attempted. And it's statement level triggers. So if you attempted to do 100 inserts or whatever during a statement, this code gets control. You can select from the inserted data and make the appropriate base table modifications. And you can see, relatively simple example, what I'm doing, I'm accepting inserts into the view, I'm getting those, and I'm redirecting them to the appropriate base table. So effectively, the view becomes 100% updatable, 100% insertable. Okay? New data types. Couple types that are, 3 types that are new here. Just a quick little bit on each one of them. First one is a table type. Table type it's driven by 2 things, I guess. The first thing that drives a table type is when you have user-defined table functions, user-defined relational functions that I mentioned earlier, you need some way of receiving the results back from a user-defined table function. Now, one way is to have it directly in a from clause, in which case you don't need to carry it around. But it turns out it's very useful to be able to run a table function, get a result back, and then operate on that result several times. And so you can run the query, get the result back into a table variable, and then directly insert into that table variable, directly select from that table variable. There's a bunch of things you can do that are kind of interesting with it. One of the things that I did recently is implement recursion using it. Same kind of thing, because I'm using the table variable effectively as a queue. So useful type. Second one's big int. This probably should have gone into the previous release. What happens as data management systems start to scale, having 4 billion rows becomes kind of a small number. And so things like count star just flat don't work. So having an 8-byte data type is absolutely imperative. And we do indeed have that with SQL Server 2000. And you can imagine all the places where it's useful. Bottom line is, our systems are scaling, and our customers are driving them hard. 4 billion is too small a number, pretty obvious. SQL variant. SQL variant's another one of those interesting little things where I've watched over the years customers trying to write non-traditional relational database applications. And this goes back to that second mantra, expanding the class of applications that can be easily written against SQL Server or against a relational data store. Now, what this class of apps did is they have, the class is probably properly called semi-structured storage. And what these apps look like, and you've probably all seen them, they have a base schema on every row that's very well known, and you absolutely know it's going to be there. But there's a bunch of fields or attributes that are dependent upon the record. They're not there on every field. And what I've watched customers do, People are very crafty when you don't give them the support they need. So what they do is they create a varchar field, possibly multiple, possibly one, and they take all of the loose schema, the schema that's not really declarable in SQL because they don't show up on every row. They convert it to varchar and stick it in there, and oftentimes they have a column that tags it, so it becomes like a tagged union. So I'm watching this, and initially you might try to explain to people that's not the right thing to do. But in fact, I mean, they got to do something, right? When you're dealing with a situation where the schema is not very well understood, you have to deal with this case. And we're seeing more and more of that. The internet, I think, brings it out in spades, in that oftentimes, especially in business-to-business e-commerce cases, but it shows up everywhere, you get something shipped to you, you get a bucket of data, and some of that data is absolutely vital, and you understand what to do with it in your application, and it lives just as it should in relational columns. And there's some of that data, you really don't know what it is, and your real job is to hold it and be able to ship it back. So having support for loose schema is a good thing. And what we've done here is SQL variant. This allows you to declare a column that has multiple data types based upon the type of object that you're storing. It's a little richer way of supporting this thing. It doesn't force customers to try a round trip through varchar. So you can declare a column of SQL variant, and on record type 1, we've got the base schema, and we've got a floating point number out there. But on record type 2, same base schema, but now we have a money data type over there. And there's absolutely no reason why we should have to convert those data types, store them directly. Those rows can all coexist now on the same table. It's a pretty powerful facility. It's just one step down the road of where we're going of supporting semi-structured storage apps much more richly and making it much easier to deal with data that's not completely understood. And it sounds sloppy when I say that. When we talk more about XML, because that's another, we've got multiple avenues that we're driving this. When we talk about XML, I'll give you a bit of a rundown of how it can be used to deal with this type of situation as well. The important thing is we deal, as we always have in the relational database world, extremely well with well laid out, properly declared schemas. Where we haven't dealt with well in the past is changing schemas that are evolving very rapidly. And that's the kind of model we're on here, and this is one of the features that helps us support that. This is that part of that multi-release plan again. Okay, talked about the internet, didn't I? This is important everywhere, but it's really important on the internet. Full text search. This is the support for being able to put documents in the database system and make requests on documents, make requests over those documents. So for example, I'd want to be looking for the name James Hamilton near SQL and find if it's in any of this, if it shows up anywhere in this relational system, in any document, the name James Hamilton and near SQL, I want to see it. That's the kind of support that it's really popular when you're starting to work directly with end users. The way relational database systems were used a number of years back is usually the experts in the data operated directly against the schema, and it's perfectly fine, works very well. In business-to-business e-commerce cases, or even more so in business-to-customer e-commerce cases, the customer doesn't really understand the schema that well, and oftentimes just wants to find something regardless of where it happens to be stored in the system. So offering them full-text search as a way of narrowing things down is very powerful. This feature is getting has been getting a lot of heavy use in 7.0. In fact, 7.0 is where it really started to get a lot of interest. And we've made a lot of changes to it in this release. Some of them with respect to how we support it. I talked earlier about non-orthogonal support being a bad thing. This wasn't supported previously in a cluster environment. Now it is. So full text and a failover cluster works exactly as it should. Second thing is we made a bunch of scalability changes in this area. One of them is change tracking. A lot of these internet apps have effectively read-only data, and absolutely not a problem. But more and more and more, there's pressure to have data online and actually changing in real time. And we need to be able to maintain the indexes up to date as well. So the way we were doing that previously is we'd have timestamps on the change data, and we'd go through, when you schedule the full text index, we'd go through and crawl the table. The problem is when you have multi-terabyte tables, that could take a long time. So the change tracking support is really quite nifty. And this goes back again to this common infrastructure, this I talked about earlier. As part of normalization, when we're doing change tracking, if you're updating a full text index column, we add to the plan the change that also updates the queue that says this table has changed. And so the act of changing the data also schedules it to be updated in the full text index as well. Extremely efficient, and scales very well to some very large table sizes. So I think this is an important extension of its support. Another area where we've extended the support of full text search in a fairly substantial way is we used to support indexing text because full text is text. But a lot of documents aren't pure text. So now we support Excel, Word, PowerPoint, and the architecture that we use to plug in different filter types is open. So if you have a specific document type or a special filter that operates on your data, then you can go ahead and plug it into this framework as well and leverage the full text search engine. So changes here have been more in the areas of expanding its use, focusing on scalability, and over the next release, we're going to continue to focus on that much higher, continue to focus on scalability as a big feature focus. Extended properties. This is more of a little thing, but it's an important little thing in my opinion. We're working with the Access team. The Access team has the world's best front-end to database. It really is phenomenally good. And what Access wants is it wants to have SQL Server as its backend. It wants to have the world's most scalable, most robust database on its backend server. Because Access is so rich at the front end, it needs to track information in order to drive the UI on an object level in the database. And so what they needed to do is they needed to be able to associate with every table in the system a set of attribute value pairs. So Access needed to be able to say, listen, with this table, here's the attribute of display width, and here's the attributes of color for font color, for example. And so they wanted support for these attribute value pairs on tables, on views, on every object in the system. So what we decided to do is, indeed, we do support that for Access because Access is a really important front end for us. But we also support it in a generalized way because if Access needed it, perhaps other customers need it as well. And so it's possible now to add attributes, name value pairs, to every object in the database system. And I think all of you, especially if you're involved in administrative roles, can think of a lot of uses to put to this. Because when you're keeping notes about things, the safest way to keep notes on things is with the things themselves. Little data integrity thing. So I think it's useful. Small feature, but useful. I've got a couple examples there of how to use it. You'll see SP add extended property. What that does is it puts an extended property on the table, employee ID, and then the next one is an example of a table function that goes and gets the name value pairs off of the object in the system. So good for Access, I think good in general as well. Other small features that are part of the relational store before we look at some of the bigger ones again, like indexed views, are checksum support. Checksum's used to very efficiently compute when there are changes by our replication team. This is another example where you'll keep seeing us make this kind of decision, is if replication needed it, if it was useful for replication, I can imagine any customer wanting to use it. So if you're going to go to the trouble of writing code, and you're going to go to the trouble of testing code, you might as well go to the trouble of publishing the interface and letting people use it. So that's where checksum came from. It gives the ability to compute a reliable checksum on one or more columns. And predominantly the use for it is change tracking. Session context. Another example of the same kind of thing. Paul Flessner talked earlier about the importance of multi-tiered applications. Some multi-tiered applications need some notion of tracking which connection they happen to be operating on right now. And the reason for that is the application servers usually try to be stateless to get extremely high scale. They get that, but sometimes they need to have some state tracking, so they need to know what connection they're associated with back into the server. Maybe they're doing server affinity. Could be a large number of reasons why I can imagine wanting to do that. One of our major vendors asked for this support. Same thing. If they needed it, might as well make it available to other customers that are writing high-scale, mid-tier app servers. And what session context is a mechanism of associating data with a given connection, so you can pull that data back in order to identify the connection or whatever you want. Other changes in this release: tool support. Profilers now supports larger workloads. Query Analyzer has been enhanced substantially. The biggest excitement for me, at least in the Query Analyzer, is it now supports T-SQL debugging. I urge you to try that. I think you'll like that one. Yeah, it's popular. Let's look a little bit about XML support. We talked about extending data stores and some of the action that's happening. I first talked on semi-structured stories and some of the changes I see happening there. Next one is XML support. XML is interesting because it's an extremely simple description mechanism, but its power comes from two mechanisms. One is, because it's so simple, it's ubiquitous. And once you have a mechanism that's available everywhere, you actually have the capability of starting to leverage tools and things like that. And so it's not so much that XML is a particularly good format. It's arguably a little fat and not that great, but it's wonderful that it's everywhere. In just the same way, it's wonderful that HTML showed up everywhere. This is going to be extremely important. And what we're looking for here, and the support that I'm talking about here, is saying, listen, XML is for real, and it's really important. And relational databases are extremely good for supporting high-speed query. So taking XML data and mapping it into a relational store is very important. Taking relational data and publishing it as XML is also very important. And there's a bunch of different variants of that. I'll just briefly touch on each one of them here. First one is select arbitrary SQL statement for XML. And there's three classes of this particular query. But all three classes share this in common. You make whatever complicated SQL statement that you want, and it comes back not as a row set, but now as pure XML. It can be published wherever you want. The three forms of support are various degrees of richness versus simplicity. The simplest one is for XML auto, and what happens there is the system recognizes by matching names, tracking referential integrity constraints, that kind of thing, and figures out the hierarchy of the table, the hierarchy to return in XML. Because as you know, this query that goes out, reaches in to the SQL Server engine and returns XML, is actually returning a shape. You have to figure out what hierarchical XML shape to return. So the first one is a simple one. It says, let us do the work. We'll track things like referential integrity and figure out the right answer. The next one is raw, which just returns it as a row set. So that goes in, makes a standard SQL query, gets a standard flat result set, but returns it in XML form. That's also useful. The third one is explicit. And in explicit form, the hierarchy is laid out precisely in the SQL statement itself. It's more complicated to write, but it is also capable of returning arbitrary hierarchies in XML. So first support, reaching into the server, returning XML. Other forms of being able to do that, but this is a good one. Other forms that I think are even, for me, even a little more, probably more important, are annotated schema. Annotated schema is the real one. I mean, they're both real, but annotated schema is the one I find pretty exciting. It gives you the capability of expressing a schema mapping. That's a mapping between an XML schema and a SQL Server schema. And that once you've got that mapping, then any query that comes in against an annotated schema will go and reach in, execute the appropriate query or queries, and produce an XML result following that mapping. So it's quite powerful. It's also quite simple. Templates, similar kind of thing. It's the ability to have an XML document with queries embedded into it. XSLT transforms. XPath is a simple query support over XML. And direct URL access. This one's kind of interesting. In direct URL access gives you the capability of defining a virtual route on the server where SQL Server is, and any query that goes into that virtual route, that spot, if you will, in the URL hierarchy, gets redirected towards SQL Server, and so you could do direct queries with URLs. So again, pretty powerful feature. You can imagine some of the capabilities that makes open, that opens up in the types of apps that you can actually write. XML to relational, that's going the other way. That's feeding from the XML side into the relational database system. Same kind of thing when I talked about annotated schema as being a way of doing a schema mapping from the XML side to relational. Same thing going the other way as well. The schema mapping is, in fact, allows you to associate both directions. Update grams will be delivered as a web release a little bit post SQL Server 2000. But update grams are an ability to send a change directly into the server as XML. I can see this being very powerful to be used in situations where you want to do app-level replication, special fine-grained replication owned by the application. To be able to fire around XML is probably a good way of doing that. Bulk load is also supported, so masses of XML documents can be brought into the server efficiently as a single operation. Here's an example. This particular example I've chosen to show it as a URL access. It's not the most beautiful thing in the world because blanks are showing up as plus and things like that. But what it's doing is it's sending a request directly into the SQL Server address space. So what happens is that IIS gets it. It's our virtual route, and so it gets passed off to us. The query gets executed. You'll notice on the tail end of that it says for XML auto. That says, oh, you want to get XML back. And it says you'd also like us to do automatic hierarchy or shaping, so we do that. And what comes back from this single query is an XML document. Again, fairly powerful. It requires you to understand XML and the schema that you're operating on, but allows whole new classes of apps to be written. And again, we'll keep driving away at that. We want to expand the class of apps that can be efficiently supported on a relational database system. Okay. Secure socket layer connection? Yeah, the question was, can we do this over a secure socket layer connection? Absolutely. Yes, absolutely. Okay, let's look at manageability. In the area of manageability, we're looking at, first one, multiple SQL Server instances. This is one of those features where it was I have to have it type thing. This is one of those ones where I just had to have it. The kinds of things that multiple instances are useful for are fairly broad. The reason why SQL Server didn't have multiple instance supports is in some ways SQL Server has a better architecture in that we have a single server on a box, we support very efficient multiple databases, and so for a lot of reasons multiple instances is absolutely not needed. However, there are some reasons why it's a very good thing. Number one, if I have a large-scale application delivered on a very expensive system, my final testing of an SP or a new release, I'd actually like to do it on the same hardware in the same environment without disturbing my customers. Yeah, I know it's the same box, and I know there's danger with that, but I really want to bring up another server on the same box and be able to run the workload beside to make sure I'm confident. It's a very good use for multiple instances. It's not that you want to go in production that way, but you want that other server running in production. So that's one form of support. Second level is there's a whole class of server consolidations or app hosting scenarios that require multiple instances. For example, what if SAP has certified on this particular version, but Bon or PeopleSoft is certified in this other particular version, and they're not the same? Kind of unfortunate, I think we ought to all work, we do all work trying to avoid those things, making sure that all vendors are supporting all releases. But when you get in a situation like that, or we have an internal app that's targeted against a previous release, you don't feel like migrating it forward, this gives you the capability of running multiple releases on the box at the same time. It's a nice, orderly way of taking your shop through time. And anytime you have a cliff transition, those are the problems, those are the times you run into all weekend working. Those are the times you run into real customer dissatisfaction. The ability to go multiple instances and slowly make transitions is very powerful. So that's why I had to have it. On one respect, I think SQL Server doesn't need it for all the right reasons, yet for some of the reasons I talked about with respect to manageability and slowly evolving into the future, taking releases one step at a time, multiple instances is very important support. Paul mentioned a third one, actually, and that is when you're delivering a packaged application, some packaged application vendors want to have total and complete control of their server, of the security on the server, and all of the databases owned by that server. If you have two packaged apps on the same box, you need to have two instances. I worked fairly hard trying to talk those vendors out of that model because it is way more efficient to have a single server with shared resources, because a single server can flow memory resources back and forth between them and flow disk resources back and forth between them. Nonetheless, I know that they need this, and there's some especially low-end apps that need to have total control. So here's what the support looks like. Now, in order to maintain backward compatibility, there's still a notion of a default server. And what a default server is just like it's always been, when you connect to a SQL server, you don't say which one. You connect to a server, and you get the SQL server on that box, and that's the same way moving into SQL Server 2000 as it's always been. The additional support that's there is, as well as connecting into a server, you can optionally specify a specific instance. So I can connect to server 1, in which case I'll get the default server. You'll see that in the middle of the screen. I can connect into server 1 / inst1, and I'll get one of those named instances above. What this allows me to do is to play with the client configurations in order to run tests against named instances and then roll over to a default instance. And a fair degree of flexibility in moving back and forth between them. In SQL Server 2000, we'll support one default instance, and I think we're testing up to 16 named instances. And that number may change over the next little while if we get customer feedback that more is important or whatever. But that's the number I think we're currently testing. No reason why you can't run more, actually. Okay, that's multiple instances. Let's look a little bit at what changes we've made in the security realm. Some of the changes in security, well, there's a question came up earlier about SSL support on the URL that comes into XML. I just said, well, yes, we support SSL on that connection. We also support SSL on the client-server connections. So one of the protocols we support now is SSL, Secure Socket Layer. We have new built-in functions that are being added to SQL Server to do encryption at a column level. What that allows you to do is to have a specific column that is encrypted, and any access to that column has to go through a user-defined function that decrypts that column. And so any inserts into it goes through the encryption function. Any deletion, any selects, projections out of that column have to go through the decryption function. The reason that's useful, there's a bunch of reasons. One of them is protection against backup administration and publishing through secondary media. Some information just has to be given to other vendors and shipped off-site. That's part of disaster recovery. Some data is so sensitive that even though all the proper data protection procedures are in place, you still want to be able to protect it with additional encryption. So in SQL Server 7.0, we will support column-level encryption. It does require operations against those columns to be mediated by the encryption and decryption function in and out of the data store. Another one that Paul mentioned earlier today is the default installation of SQL Server is now secure. We have a security screen that helps people make the right decision. And the idea behind that is it's the same thing that the Unix world went through in the mid-'80s, is if everybody knows the password on the guest account is public, well, after a while people go looking for it. And so what we're trying to do is to make the default installation of SQL Server be secure. It's a way of helping with admin and allowing people not to have to understand so many of the finer nuances of our security system in order to make sure they actually get a secure server. We also have Win2K Kerberos support, and that allows us to do delegation through linked servers. And so you come in as a client to our server, and we are impersonating the client that made that login request into the server. If you leave that server and make a request to a linked server, again, the same identity is propagated through. Pretty important support in making distributed query work properly and be fully integrated into the system. It wasn't possible for us to do this prior to Win2K. So this is a Win2K only feature. Other support, here's another one that's a lot of work. Auditing in C2. C2 is sort of the proof that you've got full auditing support. I would say the bulk of our customer workloads, auditing is not that important, but there are some where it's life and death. Federal accounts is a beautiful example. What auditing allows you to do is to track changes that are made to any object in the system and failed attempts to get access to objects in the system. So failed logins, failed attempts to touch, security violations in general get audited. It's important for those systems that are available, especially in extranets, where it may not be just your employees that have access to the data, but it might be some partners that have access as well. If you have the ability to track attempts at illegal access, you've got a chance to better control the data and do a better job of managing it. And part of the auditing system, of course, is getting the federal C2 authentication and evaluation, pardon me. And that's been a bear. Let's look at scalability and performance. We've made a bunch of changes in this area. It's an area that's near and dear to my heart. I said that a couple of things were coming up. One of them was partitioned views. Partitioned views is extremely powerful in that it allows you to create a view over a union all table. So it's the same kind of example we talked about before, except there's some additional constraints placed on this one. If you look at the example, you'll see check constraints. Each table that's declared, we're declaring a base table, base table, base table. Each base table is declared to hold a subset of the range of possible data. So if you look at all of the tables together, all of those base tables together, that forms the entire table. Each one's a disjoint subset. And so we went back to that example earlier. I said, well, you could have the January data here and the February data here. Everybody knows it has a real administrative advantages to be able to roll January data off while you're putting next month's data back online. It's a wonderful facility from administrative purposes. It also has some scaling advantages that I'll show you as well. Because one of the beauties of SQL Server is we support distributed query in all of these. And we talked about orthogonality of function. These views could be on different systems. So in addition to the administrative simplicity that comes with being able to roll months off one at a time and have a common view, we also have the scaling potential, and I'll show you some of the advantages of that. I've seen this used in a couple different places. One of the most common ones is multiple systems. For scalability reasons, they're partitioned, and so very large sites, and most of the operational access goes directly against the appropriate server. But the company's looking for some way to do aggregations and to do data mining across all of the servers. So you have to some way to do report generation across all those servers. Well, you could hand code all of that against each individual one and hand aggregate in the application, but it's really a pain. What this allows you to do is to have a view laid over top of all of them and run queries against that view. Okay, so on this particular example, we've got a union all view. The base tables have discontiguous, mutual exclusive ranges. And so what does that look like? Well, in this example, you'll see what we're doing is each system, I told about the distributed query support, Each system up there has its own subset of all of the data. And because each one has its own subset of the data, and I declare a view on each system that includes all of the data in the entire system, what that means is you could connect to node 1 and make a selection against that union all view, and you don't care if you're asking for data on node 1 or data on node 3 or on aggregations of data across 4 different nodes. We handle it ourselves. And the optimizer does 2 things that are absolutely key. The first thing is partition elimination. And what that means is the worst thing in the world that could happen to you is you've got a beautiful partition system, so it scales really well, and every query goes against every system. Now, that didn't scale. So the first thing the optimizer does is it says, listen, I know that you're only going after these 2 systems, and so I'll squeeze down the number of systems that are involved to only include those systems that are touched. And to be honest, most competitors have figured that out. It's a good thing to do. We ought to all do it. Okay, that's done. Second form of partition elimination I think is really powerful is dynamic partition elimination. And it turns out, more often than not, the partition key, the actual key that you're asking questions about, the range that you're asking questions about, oftentimes is not known at optimization time. But it sure as heck is known at runtime. And so what dynamic partition elimination allows us to do is to say we compiled this plan such that it was capable of executing on any node and every node at the same time in the system, but your particular query only accesses 1 node. So how many nodes do we touch? 1. Without that last feature, that feature of dynamic partition elimination, this is interesting and it is very powerful, but it doesn't have that beautiful scaling capability that you get with dynamic partition elimination. So has everyone got this? We've got each system having a 100% symmetric view. Each system has its own tiny slice of data. Each system sees all the data in the system, in the virtual cluster, I should call it. How is that done? Well, on each server, we're adding linked servers. So each server has to be told about every other server. Each server has to have its slice of the base data created on it, and each server has to have the view created on it. Here's what happens. This is the TPCC result that we just ran, and here's what it looks like. This was taken from the full disclosure report. What it is computing by the slice. Because I've got a partitionable workload, and remember, not all workloads are as clean as this, but there's a lot of workloads that are. If you have a workload that can be broken up into ranges like that, and I haven't talked to a .com yet that wasn't the case of, almost always you can find this. If it has beautiful little partitions that you can break the data upon, what that means is you can do what I just described to you and break it across multiple systems. Okay, computing by the slice. If you don't have enough nodes, just add more. You say, well, does that scale? And the answer is absolutely. If the behavior of your app before was to touch a small number of nodes, and you add 12 more nodes, the behavior of the app after that is to touch a small number of nodes. So it scales just as well after as before. So you can control the amount of data that's stored on each system. It works. This is the example. This is a killer result for a couple different reasons. I've been doing these benchmark things or involved with them for, I don't know, 10 years or plus, probably more. And the way the benchmark game is played is this. This is a TP benchmark. Here's how you learn to be a hero in the benchmark world. What you do is you take the system that you're trying to optimize for. You add disk to that system until you're no longer I/O bound. You'll watch the CPU load climb to 100%. When you hit 100% CPU load, you've got enough I/O, stop adding disks. Usually the benchmarks require more disks than you need, so in fact you don't have to even play that game. You've already got enough disks that you can load the CPU entirely. Focus on path length, the job's done. It's a path length game. That's all it comes down to. And that includes the I/O path length to do I/O. I mean, that I/O doesn't really kill you because I/O is latency. Making the latency requirements on TP benchmarks usually not hard. The hard part is the path length. So always they're running 100%. Both these benchmarks are running at 90%. Now why the heck would we not drive them at 100? wasn't worth the trouble. The 8-way run, it's absolutely true. The 8-way run, I've never seen this before. I giggled when I first look at it. It feels like we're not trying hard enough. But it doesn't matter. The 8-way run was a major celebration. Paul talked about it earlier, because the team that did this work had produced a number that was bigger than any other number in the world. And for me, this was really exciting, because when I started in this business, I was doing work on System 390s. And I caught on real early that was not the future of computing. These $30 million boxes are not the future. I knew Unix was the future. And so all through the 80s, I built Unix boxes and laughed at the dinosaurs working on those old things. And it turns out, yeah, I was a dinosaur too. The real right answer is commodity systems. And the only thing that keeps us away from commodity systems is the software has never been good enough. It's bottom line. The reason we run big systems is because we don't scale well enough on lots of small systems. So this is the first step towards, basically where I think the entire world ought to be going. Buying expensive systems makes no sense. You should have large numbers of cheap systems. Software should be where the brains are, and smart software. I told you a couple tricks we do, and there's millions of others waiting to be done. Every time software gets smart tricks, it makes wider the class of apps that can take advantage of this type of scaling a reality. The beauty behind this is the 12-way number. What did it take to do a 12-way number? Compaq was the biggest contributor. I mean, I don't want to downplay the contribution of the team that was working all night, several nights in a row, but benchmarks are huge efforts. Compaq got the hardware together. This has, I forget how many terabytes of data. It's just astounding. It's just thousands of disks. So the hard part is getting all that data together. And it's a real statement of the quality of a Compaq system, that they can get all that software, all that hardware together, and it actually works all at the same time. It's, these are good systems. The amazing thing is there's a few days between that 8-way result and the 12-way result. It scales. Just plug in more nodes. What if, just say that Sun came out with a 128 processor box, and it actually did scale. And so this number that Sun produced right there, that cost $10 million, so say they came out with a $30 million answer. Well, could we add 12 more nodes? Yep. What's the limit on how big a bar would you like? The answer is, how good's your air conditioning? How big's the machine room? This benchmark actually scales. Does this apply to all workloads? No, it doesn't. The workload has to have the characteristic of having a well-defined partition key. We already talked about that. That's not that rare, but not every app. And each application can't touch all data. The apps themselves have to touch a subset of the data. Not all apps, but a good many. Computing by the slice. Jim Gray's been talking about it for as many years as I've known him. It's starting to happen. In my opinion, it's starting to happen maybe 10 years later than I might like, but it's starting to happen. And I see numbers like this, I get excited. Not so much because of the bigness of the number, although it is unbelievably big, but because of the combination of how little investment in time was put into getting the number, which talks about ease of use. And the second thing is how cheap it was. Finally, we're getting affordability. Yes, you had a question. Yes. Could you, if you have a little bit of a longer question, maybe you could step to the microphone?
Say regarding scalability, okay, I have a database where I can divide my logins by the first letter of the alphabet. Like I say, I have logins, partition 1 will have letters A, 2 will have, like from A to Z, I have 26 partitions. Now what I find is the node which is having A is getting overloaded.
Yes.
How do I scale with that? You're saying add a new node. How do I add a new node? I have to physically divide this database, right?
Right. There's two tricks to go. There's two ways to approach that. One of them is to say, actually, the total virtual cluster is fine. There's nothing wrong with it. What I need to do is I've got a hotspot. The Z's aren't that hot, and so I need to change the partition. So the way that's done is by moving some of the data off the A server. So and the way you make that decision is you know that you have to think a little bit and know that it's coming. You wouldn't partition on A. You'd partition on a function of A such that when you make that change of the data partition, that the apps just respond and connect to the right thing.
So, but basically, whenever you're saying that add another node, it is not as easy the way you just say it.
Absolutely not. You're 100% correct. And so the two things are you have to think ahead and well, first of all, you have to have partitionable workload on a partitionable data set. And that's not the world. So this is not the solution to the world's problems, but it is some. Second thing you have to have is when you have to anticipate you're going to be wanting to make range partitioning changes over time to deal with data and query skew. Absolutely true again. So the trick with that is this is only step one. We could make this much easier to adapt over time. And you bet. Count on it. So let me move on. I've been talking a little bit about performance. Is there a question?
Yeah, I had a question about the parallel views.
Yeah.
Obviously, you do parallel scans across multiple nodes.
Yeah.
I was curious about how far you've taken that. For example, can you do parallel joins across nodes, hash joins, star joins, things of that nature across multiple nodes?
Right. We can today do, with every query that goes to every node is executed in parallel on each of the nodes. The support, I don't think, went in. We actually spent some time on it early on in this release, is to be able to send parallel requests out at the same time. I'm pretty sure that's not in there, but it's extremely doable, and we understand the problem. So
the other thing is, are there a maximum to the number of nodes or the number of tables that you could union?
Tables.
Like, for example, tandem, typically on a single node you have 16, nodes that you
Right,
like sort of link.
right.
I didn't know if you had a similar limitation.
No, I know the tandem architecture a little bit, where you have admin groups of 16 and then super
And then you can
groups.
max up to 4080, right?
Right. I can't think of it. I think you'll run into real limits before you run into system limits, I guess is the right answer on that one. 5 minutes? Super. Okay, index views. Index views is the last thing that's really important for me to cover. I can be flexible on the rest, but I got to cover this. Index views. What's the right? Here's the way of thinking about index views. Here's the problem. What's the biggest disk drive that's available today? I usually look about once every 6 months. Yeah, so I hear numbers like 16 gig, 17 gig, and I always amaze myself. 73.4 gig. Seagate Sheeta, huge disk. It's absolutely monumentally big. And it's a 10,000 RPM disk, 5.6 millisecond seek time. So it's phenomenally big and phenomenally fast. Sounds like a wonderful disk. It's a very good disk. The killer with this is do one form of math. This is a distressing form of math. And that says, how many accesses can this disk support per gig? And the answer is, it's about an access, it's a couple accesses per second per gig. Couple, 2.3, under 3 accesses per second per gig. So if you think about what that means, if you have a relatively random workload traversing over the data, these very large disks, even though they're monumentally fast, are actually becoming black holes. It's extremely difficult to get the data out of the disks. So it's an interesting problem to face as a database developer, is you have huge devices, yet their access times are terrible. Just worse, unbelievably bad, in that the spindles, the mechanicals are speeding up at a rate so much slower than the density in the disk itself. We've got a real problem. So lots of storage space and small and very difficult to get access to it. What we need is ways of getting the data denser, because I've got the space for it. I've got space for multiple copies. Here's where materialized views come in. 2 different ways. One way, what a materialized view is a view that we actually pre-compute. And so if you have a view over various aggregations, and it happens to be a very expensive join, lots of aggregations involved, you can pre-compute it. And the advantage of pre-computing it is if you make selections, it doesn't have to be recomputed. It can be selected from this materialized view. Now, if I have lots of storage, I have the capability of storing more of these. Yes, there's downside you have to balance against, is that you have the cost of maintaining the views versus the advantage of fetching from them. But it is surprisingly powerful what can be done with these things. So if you think about it, if I have a six-way join with lots of aggregations, and I've got a base table, if that query would have taken 4 minutes to operate, if I instead run it against the view, I can now answer the question in sub-seconds. Very powerful, especially in read-mostly workloads. The problem is the work it requires. Every time you think hard about an application, you write a new view, you'd hate to have to rewrite the applications to use the new view. And that's the beauty behind this, is that you can create an index view in the exact same way you can create an index, and you can send a query against the base table, and our optimizer, thank you Cesar and Nigel, is smart enough to say, wait a second, I already have that answer, and redirect the query against the view. And so with no app changes at all, we're steering it towards, we're saying, I recognize that you are actually asking the same question that we've already pre-computed, and the view substitution takes place, and it goes after the stored view. Now, over time, you discover that, for example, that view was inefficient. It's too hard to maintain. There's too many changes going on. So you created a little bit simpler view that still gives great query speed, but doesn't cost as much to maintain. It's a standard indexing tuning type problem. You don't have to change the app. The app now steers to the new one. The old one goes away. It works fine. Here's an example. We're going to create and populate a table called sales. We're going to create a view in statement 2. In statement 3, I'm going to create an index on the view. That's the first place where we're starting to see something new. I've created a view that describes an arbitrarily complicated query. Now I'm creating an index over that view. So I say create unique clustered index over iView. So here's where it pays off. You see the select on the bottom? Select top 5 from store ID, some group. The optimizer says, wait a second, I've seen that before. And even though, if you look at that, you see that that query is against the base table, it gets redirected against the index view. Here's the plan that actually gets executed. So I did a query against the base table. The base table is not even mentioned in this query plan. Query execution, when it ran, didn't do a sum. There's no aggregation here. There's no base table access here. It got re-steered to go after the index instead. So what we end up with is index-only access on a trivial table, running top on that and returning the result. It's a very nice-looking plan. And the beauty behind this, if I change that view, the optimizer will figure it out and say, okay, I'll use a different index view if you've created a different one. Or you can not have an index view at all, and the app still doesn't change. It just runs a little bit slower. Here's a really nice example. This is some work that Lubor Kohler was doing. And the reason this is a nice example is when we started this work, I said to Lubor, when we started working on index views, I want to make sure they're real. I want to make sure that index views are actually usable. And so what we did, our sales guys maintained very complicated databases of customer buying habits and the number of windows that were sold versus the number of exchanges that were sold, and they do complicated pivots and who knows what. The queries are hellish. And so it's a beautiful example of a real tough workload. So what we said is, he said, listen, Lubor went to work with these guys and said, listen, I'd like you to put in beta 1 in your production system, and I'd like you to try to use index views. And here's the results he ended up getting a couple months back. Just phenomenal speed ups. The blue top lines are how long these queries took to run before. And we used to use those numbers as a way of talking about how good our optimizer was, because to be honest with you, we're proud of those numbers. It's good. The numbers along the bottom are using index views. And it's a real application, so they have to balance the cost of view management against the advantage of fast queries. And so you can't just create the richest view possible, because it would cost too much to maintain. This is an example of real app guys thinking hard and deciding how to tune the system. Good stuff, but not good enough. One step further is we have the index tuning wizard. Well, this is an indexing problem. That's why we call them index views. The index tuning wizard is now capable of making recommendations on index views to create as well. Alrighty. Let me close off by talking a little bit about large memory support. We're getting a little bit short on time. Two forms of large memory support that are showing up as a result of Windows 2000. The first one that's on the top there was the support that was delivered in SQL Server 7.0, and it's support for greater than 4 gig or greater than 3 gig buffer pools using a device driver copy in, copy out model. What we have available now is, with Win2K, is 3 different ways of exploiting large memories. The first one requires no server changes. Each server gets its own 3 gig address space, but if you're running more than one server on the box, the fact that the box has perhaps could have 20 gig or whatever of main memory, will exploit it through multiple servers. Good support, no change required to the server. Next level support below that is, okay, what about a single server exploiting that large more than 3 gig or more than 4 gig memory system? Well, again, instead of having the previous model that we had with the last release that was doing copying is very cache unkind. This one is doing remapping. It's using the NT virtual memory manager to map pages in and out of the buffer pool. Much more efficient management. The final one is full 64-bit support. And the only reason I wanted to bring it up is shortly after Win2K ships, there's going to be a 64-bit version of Win2K shipping, and SQL Server is running on it today and running very well. So I'm going to close off. I've talked a lot about features throughout this release. I've talked a lot about velocity of change in this release because you can keep expecting the same velocity of change. I want to close with, look at the work we're doing on scaling. We've now got hardware partners that have, in our shop, 16-way SMPs. We have 32-way SMPs coming, so the hardware's coming. We have 64-bit memory, so the memory sizes are coming. And I've talked about a lot of our scaling features, which again they're not coming, they're here. So listen, thank you very much for your time, and it's been a pleasure to tell you a little bit about what we've done during this release. Thanks a lot.